a IR spectra, is the functional group determination. So the reason I mention that is because NMR can show you both the functional groups that are present in many cases and the structure at which they're bound together, like what fragments are bound to what other fragment. So as a general tool, NMR is by far a lot more powerful than IR, but IR is used to corroborate the information that you get from NMR just to provide more support. So again, that's kind of why I'm going to briefly go over it here, because it's more of a supplemental tool instead of the main experimental evidence. So how an IR looks is it's drawn down like in this this drawing here, where you have transmittance on this axis. So and it's expressed in wave numbers. So you have wave numbers on this axis, which increases going to the left. So first of all, something I should mention, a wave number is inverse centimeter, and it's related to the wavelength. It's the inverse of the wavelength. So the reason that we do this, when I first learned this, I was like, why do we bother to show it in wave numbers? It seems like we could just express it in wavelength and be good enough. But the reason they do this is that this is proportional to energy. So in essence, you can think about this as energy. So increasing wave numbers, or moving to the left on this diagram, is effectively increasing energy. And that's useful because it tells us information about the types of bonds that are showing up in that peak, because the energy is related directly to the vibration of the bonds, which is ultimately why we're seeing peaks. So what this would look like experimentally, you're going to see this is like at 1,000 and then 2,000 and 3,000 wave numbers. And what you're going to see before 1,000 is a mess of stuff. You can't get much information from here. There are some things that you can get out of that. This is what we call the fingerprint region, lower than 1,000, but it doesn't give you a ton of information. So there's that. And then at around 3,000, right before it, there are strong peaks, and these are carbon hydrogens stretching of an alkane. So any organic molecule is going to have CH stretching pretty much. So basically what I'm saying is you're not going to get a bunch of information from right at 3,000 or before 1,000. The key information that you're going to get is between this 1,000 to, let's say, 2,800. So in this region, and then above 2,000, or sorry, above 3,000, right? There's a couple of key characteristic peaks that show up in those regions that can tell you a lot of information about your functional group. So basically the takeaway from what I've talked about so far is pretty much ignore what's before 1,000 and then pay special attention between 1,000 to 3,000 and or 1,000 to 2,800 and then above 3,000. Okay, questions on that? That's a brief introduction. All right, so now this part is going to be dense because it's simply the list of key features, key characteristic peaks that you just need to have memorized or have available to you when you're answering these questions. So I'm going to start from the highest energy and move down. That's just how I've organized my graph. So here's the first column is going to be frequency, and then the intensity. So the intensity is how much is transmitted. So how far down the peak goes in your IR. So if this is strong, then it's going to look like this, where it's going all the way down to 100. If it's medium, then it's like this. And if it's weak, it's something like that. Just to give you. So this is what I'll call W, this I'll call M, and this I'll call S for weak, medium, and strong. And that's what will be in the intensity column. Okay, so the first one to talk about is the OH functional group. And this frequency appears between 3,200 and 3,650. And this is pretty strong, but it's broad. So what that means is the peak, it won't be a narrow peak, it's going to be very wide. Nitrogen, hydrogen occurs essentially in the same region, 3100 to 3550. And this is a medium intensity, but it's sharp. So that's how you can distinguish between an OH and an NH is one, the intensity is slightly higher and it won't be broad if it's a nitrogen hydrogen bond. And then like I started with, carbon hydrogens of an alkane are right at 3000, 2900 to 3000. And these are usually medium to strong. They're just, it's kind of a mess in that region like I was alluding to at the beginning. Then you can have the carbon hydrogen of an alkene. This occurs above 3000. This is why I said the above 3000 is a region that you should definitely keep an eye out for, because that gives you more information than the fingerprint in other regions. The alkyne occurs between these regions. And what I mean is between the alkene and the OHs and NHs. And this is a weak stretch around 3300, you know, give or take 25 wave numbers on either direction. Then we have our carbon-carbon triple bond of the alkyne. This is between 2100 and 25 or 2250. This is also weak. So notice that both the alkyne stretches are weak. And then we have a carbon-nitrogen triple bond. This is 2200 to 2250. This is medium strength, and it's usually pretty sharp too. And then we have, that's basically it, except, we have a carbon-carbon double bond. So I forgot about this one, which is 16 to 1680. This one's also medium. And then we have the carbonyl. And this is the most ambiguous one, because there's so many carbonyl stretches that you can have. So the carbonyl is somewhere between 1630 and 1820. And all of the carbonyl functional groups can be in that range. So like if you had a carboxylic acid, that can be in that range. And if you had an aldehyde, that can be in that range. So they vary somewhat depending on what they are, but they're always in this range. So I think it's best to not memorize what all of these individual functional groups correspond to, but it's better to just know that this is the carbonyl and then use your NMR or your other data to figure out which type of carbonyl it is, because the IR for the carbonyl can be somewhat ambiguous, but you'll notice that it is a carbonyl because the region between a C carbon-carbon double bond and carbon-oxygen double bond are partially overlapped, but the difference is the carbonyl is always going to be strong compared to the medium intensity of the alkene. So, sorry I had to put you through that. I know that's dense, but can I just put this in one frame? Yeah, I can try. I should be able to zoom out. Yep. So I know that was pretty boring, but you need to know those. But anyway, that is the all of IR that I'll talk about. I'll give you a couple examples that you could see on your homework or the final, and then we'll move on to NMR, which is the more useful of the two experiments. Okay, any questions here? And we'll get into examples. Okay, not seeing any, so let's jump into it. So the question, all right, so the question is, how would we distinguish these two based on IR? And there's like a lot of answers that you could say. So the first thing I noticed is we have an OH group, right? So if we look back at our chart, an OH group has a very distinct broad peak. So I'd say broad signal at 30, I don't know, let's say 33 or 3000 plus. because it varies between 3200 to 3650. That would be a very telling peak that we have the alcohol. Whereas here, we're going to have two distinct peaks. It'll be the carbon-carbon double bond, which is at 1600. Again, these are always varied, but somewhere in that region. And then we'll see the carbon hydrogen stretching of the alkene, which is above 3000, between 3000 and 3100. And this will be different than the OH peak because this one's going to be very broad. So my artistic skills aren't the best for representing spectra, but what you're going to see for the OH peak that's going to be useful is around 3000. You're going to see a peak something like this. So this is like 3000 here. And then this, here's like 4000. So it's going to be somewhere between that. And then, or 2000 and 1000. Right, so we're looking for this very broad peak that tells us we have the alcohol. If we were looking at the alkene, what we're going to see is a medium intensity group here above 3000 for the CHs. And then we're also going to see the carbon-carbon stretching between 1000 and 2000 that are as medium in intensity. All right. So I think that's enough for IR. You can, it's basically just interpreting this table and applying it to the functional group that you have. The only thing is you should pay special attention to if an alkene or an alkyne is terminal. So like in this case, this was terminal, which means that we have CHs that are going to stretch. But if we have an alkyne that's internal, like this one, there's no CH of the alkyne. So all you're going to see is the carbon-carbon triple bond stretching at like 2100. So that is a key distinguishing feature between an internal and a terminal alkyne like this, because here we're going to see the CHs of the alkyne at 3300, and we'll see the carbon-carbon triple bond stretching. So these two coupled together tells us that we'd have a structure something like this that has a terminal alkyne, whereas if you only have this peak, you would think an internal alkyne. So questions on that? Otherwise, we'll jump into NMR. All right. Not seeing any, we'll get into it. So there's two kinds of NMR that you'll be responsible for. There's a lot more than that, but we always start with these two. There's Proton NMR, which is just hydrogen, neutral hydrogen NMR, and there's C13 NMR. And just like with IR, I'm going to focus on how you interpret NMR data and not why NMR data or why NMR works as an instrument. Again, the book does a very good job of explaining that, but I'm not going to spend, since we only have an hour, I'm not going to spend the time doing that. So Proton NMR is far more useful. You can get more information from Proton NMR, but C13, again, similar to IR, it corroborates what you get from the Proton NMR or confirms the evidence that you see. So we'll start with Proton NMR because it's the more useful and also more complicated one. So in Proton NMR, there are 4 key features that you need to understand, and I'll break them down. So first is chemical shift, which is abbreviated as delta. And then secondly is the integration, which is just, you won't have to do any integration. It's not like calculus. It's just determining the area under the peak. So this tells you how much hydrogens are corresponding to that peak, basically. And you won't have to do anything about the integration part. It will be done for you and it'll tell you how many hydrogens, but you just need to know that that's what is meant in this part. And third, this is perhaps the most complicated. This is the splitting of your peak. And this follows an n+1 rule. And we'll talk about that last because it is definitely the most complicated part. And then there is this coupling constant, J, which this basically will tell you if like if something is cis or trans. So whether that be a ring like this, or if it's a double bond like this. So, but again, we won't stress on that. That'll basically just be something that you'll need to memorize what the constants are that correspond to cis and trans. Okay, so we'll start with chemical shift. So the chemical shift will vary depending on what's bound to the particular hydrogen. So since we're talking about proton NMR, we are describing the splitting, or not the splitting, I shouldn't say that, the peak that corresponds from the hydrogens. Right? So what we're going to see is peaks for all of these hydrogens. So one thing to point out before we get into chemical shift is hydrogens on the same carbon don't influence each other. So what I mean is, like, we're going to see one peak for all three of these hydrogens that'll be integrated to 3 hydrogens. That's why we talk about integration. So this one is going to be it's going to be one peak with 3 hydrogens, right? It's not going to be 3 peaks integrated each to 1 hydrogen. So that's the same for all of these. So like this carbon is going to have 1 peak, 2 hydrogens, and then this carbon, 1 peak, 2 hydrogens, and this carbon, 1 peak, 3 hydrogens. So there's a total of 4 peaks for the total hydrogens, 3, 6, 8, 10. For the 10 hydrogens, there'll be 4 peaks. 2 of them will integrate to 3, and the other 2 will integrate to 2. Okay. So now let's get to the chemical shift. So whenever a hydrogen that you're interested in, so again, let's look at this one, is bound to something that's electronegative, it will shift it will move the chemical or the signal upfield. Or no, it moves it downfield by convention. It moves it to higher numbers, which is downfield. Right. So let me re-explain that step by step. So these hydrogens that are bound to an electronegative atom like oxygen will be shifted to larger numbers, which is by convention called downfield, which is confusing, which is why I messed it up, because if you think about going to larger numbers, your like intuition should just say that's upfield, but that's just not the convention that chemists use. If it's shifting to higher numbers, then it's called downfield. So these hydrogens are going to be larger chemical shift compared to like these ones, because these hydrogens are only adjacent to another carbon, which is not electronegative. So it's not shifting the peaks downfield. They would just stay where they would normally be. These hydrogens here are going to be shifted because they're adjacent to the oxygen, just like this one is. And then this one is going to be not significantly shifted because it's just bound to the 2 carbons, which both are neither electronegative, significantly electronegative. This trend also applies if the carbon is a part of like a double bond, because then we consider that double bond to be somewhat electronegative. So like if you considered a vinyl proton like this proton would be shifted downfield compared to just a single bond, because that double bond has more electron density than the single bond. So this one we would expect to be larger number further downfield than the alkane that I showed there. So questions, I'm sure this is very confusing. NMR is always a very difficult thing to introduce, but bear with me as I go through some examples. I think it'll come together, but I'm going to try to build each step so then we don't we can actually interpret NMR, because if you just jump into interpretation without going through this, it can be even more difficult to follow. And by the way, I meant to start with this figure, but I forgot about it. On Appendix 4, you can't see this very well, kind of. It shows all the distinct chemical shifts. This is in your textbook and towards the back of the book. It shows the distinct chemical shifts for certain protons. So like, for instance, if we look at this, ignore the first two. Those are those are exchangeable protons. We have to talk about those. They can vary a lot. As you can see, it's 1/2 to 6. So that's a big shift. But these other ones, like a methyl group that's bound to an R group, is around 1. A CH2 group bound to 2 R groups is around 1.5, and so on and so forth. If we look at our oxygen example, that's like this. That is around 3 to 4. So again, these are always ranges. So it's just how you can interpret the range. So anyway, we'll jump into the next thing. And the next thing is splitting. And this is perhaps the hardest part. So the rule really is that neighboring hydrogens split each other. And by neighboring, I mean directly adjacent. And what splitting means is it changes a signal. So this would be like just a peak that has no splitting. A split peak would have multiple. It would split the peak into 2 peaks, basically. So neighboring hydrogens have this effect on the hydrogen signal. So how they split is n+1, where n is equal to the number of adjacent hydrogens. So n+1 is the number of split peaks that you see. So in this case, the total number of peaks, n+1 is 2, because we see 2 peaks here. So the number of adjacent hydrogens to this is 1, because now n equals 1. N is the number of adjacent hydrogens. So a peak that has 2 tips is going to be considered to have 1 neighbor. So, and you can continue this trend. If we look at a triplet now, that would be like this. It has 3 peaks. This n+1 is 3. So n is 2. It must have 2 neighboring hydrogens. So let's look at an example now. Let's not start with this, actually, because it has another feature that we need to talk about. I need to make it asymmetric. Yeah, this works. Okay, this is fine. Okay, so let's look at our carbons, number them. Again, this is proton NMR, so we're interested in the protons and how they split each other. So we consider the protons on carbon 1 and the protons on carbon 2 to be adjacent, to be a direct neighbors. So if we look at carbon 1, the hydrogens at C1, okay, they have 1 neighbor, right? It's this one. So so n equals 1. That's the best way to say it. So n equals 1. So the splitting is n+1, which is 2, right? So this peak is going to be a doublet for carbon number 1. So the hydrogens at C1, which is there. So hopefully that's clear. So the hydrogens bound to carbon number 1 are going to be a doublet, and this will integrate to 3 hydrogens. So what you're going to see in an assignment or something would be a doublet, 3 hydrogen doublet like that. It tells us that we're looking at this carbon. And I'm not showing the chemical shifts here just to simplify, but we'll tie that all together once I go through each one. So then at carbon 2, this now has multiple neighbors. Well, multiple neighboring carbons, right? So at carbon 1 and carbon 3 are both directly adjacent to carbon number 2. So there is this additive effect for splitting. So the total number of neighbors at carbon number 2 is 5, 3 of them coming from carbon 1, 2 of them coming from carbon 3, hence the total of 5 that I gave, right? So hydrogen at carbon 2, N is 5. Again, 3 from carbon 1, 2 from carbon 3. So this would be N plus 1 is 6, and this would give you a sextet is the splitting pattern. So 1, 2, 3, 4, 5, 6. It's going to look like that. 2 hydrogen sextet. Once you get above a quintet, which is 5, it becomes difficult to distinguish because sometimes experimental data, these like trailing peaks here on the edge are hard to distinguish. So sometimes people just call this a multiplet. And that's not very useful for figuring out the number of neighbors. So what you do in that case, if it's defined as a multiplet, is you have to look at the other signals that are more clear, like this doublet, and there's no ambiguity there. That has just one proton neighbor, and therefore it's a clear peak, whereas the multiplets may be unclear, but you can use the clear ones to piece your molecule together. Okay, so let's look at carbon 3 now, moving along in order. So I'll let you answer. How many neighbors does carbon 3 have? Yeah, good job, Tamara. There's 4, right? 3 from carbon number 4 and 1 from carbon number 2. So N equals 4. So N plus 1 is 5. So in an ideal spectrum, this would be a quintet. The reason I say it like that is just because I mentioned that it might be hard to distinguish this as a 5-membered peak as a quintet. But you would see, ideally you'd see that, and it would be integrated to 2 hydrogens for the 2 hydrogens that are at carbon 3. And then hopefully this can stay in frame. So the hydrogens at carbon 4 are last, and they have 2 neighbors. So this one becomes a little bit easier than the last 2. So this is going to be a 3 hydrogen triplet. There's our triplet and integrated to 3 hydrogens. All right, any questions on that? Now what I'll do is erase and then redraw the molecule and then like simulate the entire spectrum that you could see. And by simulate, I mean I'm just gonna poorly draw it to hopefully illustrate the point. All right, so let's do that. Okay, so the only thing we hadn't considered in our representation that we were doing before is the chemical shift. Okay, so this is where we would need to use our appendix, or once you have these memorized, you'll just remember them and pull them out. But here, what we're looking for is stuff bound to chlorine, because that's the key distinguisher for this molecule, right? We have a carbon bound to chlorine, everything else is not bound to the chlorine. So we would expect carbon 2, if we're staying consistent with what I showed it before, carbon 2 should have the largest chemical shift, should be the most downfield. So we would expect that, looking at our sheet here, for it to be around 3.7 or so. Notice that this isn't identical to what we have because this is a CH2 group and we have a CH group. So we would expect our CH group to be slightly more downfield than the CH2 group. So I would expect our peak hydrogens at carbon 2 to be around 4. And again, we know that it's all the other stuff that we already determined, that it should be a sextet, and there's 2 hydrogens that it'll integrate to. Okay, and then now we have to think about carbons 1 and 3. Carbons 1 and 3 are adjacent to the carbon that's bound to the chlorine. So it's adjacent to carbon 2. So that's going to shift them slightly downfield compared to if it was just a normal R group. So if we look at a methyl group, CH3, that's bound to just an R group, it's supposed to be around 1, but it's going to be more than that because it's bound to this R group that has a chlorine as well. So there is some kind of long range effect that this chlorine has on the hydrogens. So we'd expect the hydrogens at carbon 1 to be around not much further than 1, but maybe 1.3 or something. They're going to be shifted slightly due to the chlorine. And then at carbon 3 now, similar idea. We're going to expect it to be more shifted downfield than normal because it's bound, the R group has a chlorine. So again, there's this long range effect. So if we look at our CH2 bound to 2 R groups, which is just like what we have here, the CH2 bound to 2 R groups is 1.2 to 1.4. So again, I'd expect this to be like maybe 1.7, slightly more because of the carbon, or the chlorine, excuse me. And then carbon 4 is finally consistent with what we've seen before. It's the R group. This is too far away. The chlorine's too far away to have any effect on the shifts here. So we'd expect this one to be around 1. So let's, now I'll draw the spectrum as best I can. So what you would see is chemical shifts here on the x-axis. And I'm going to blow up a little bit, zoom in on this region here, because this is where most of our stuff is happening. And then I'm going to change our scale here for 3 and 4. So hopefully that makes sense. I'm expanding a certain region of it. In a real spectrum, it would be equally spaced, but since I have to draw this with a not super fine tip marker, I'm going to try to make it as clear as possible. So starting in order, our C4 is going to be around 1, and it has 2 neighbors, so it's going to be a triplet. So that's going to look like this, and it's integrating to 3 hydrogens. And that would be listed on the spectrum for you. Then if we move, next would be carbon 1, and this is going to be a 3 hydrogen doublet, which is around 1.3, so slightly higher. And it's 3 hydrogen, so you would expect the intensity or the top of the peak to be about the same for these two. And again, my illustration isn't perfect, but these should be equally tall because of the integration factor. And then, wait, did I do something wrong? No, oh, that's right. So this is carbon 1. This is carbon 4. Okay, that's right. All right, cool. All right, so now carbon 3 is at 1.7 because this is the one that is bound close to it's a CH2 group close to the chlorine. So this is a quintet. So I'm just going to draw it like a multiplet. It would look like a mess like that. And this one should be a little bit smaller than the other two because it only integrates to 2 hydrogens. And then around 4, so this is carbon 3. And then around 4, we would see the another multiplet for the 2 hydrogens at carbon number 2. Okay. So questions on that? I apologize that my illustrations aren't the best, but let's see here. I can zoom out so you can see the whole thing. So now I'll show you what a real spectrum looks like. I have an example here. You won't have to do this, I would imagine, like what I'm about to show you, but it's useful just so you guys have an idea of what this stuff actually looks like. Okay, not seeing any questions, so we'll jump into this next exercise. Okay, so this is actual things that you would see for along these lines. So, okay, so you're going to see a mass spec, which you don't have to interpret at all. It's just going to tell you chemical formula, so C6H10O4 in this case, you'll see an IR, which again can only tell you the functional groups. So in this case, we see this is a carbonyl peak. So, and everything else is basically not useful for figuring out what we have here. So we have a carbonyl, we have C6H10O4, and then you move on from that, and that's all you can really take from what we've looked at. Then you move to the proton NMR, and this is where we're going to see these signals. So this one here at 1.5 is a doublet, and then at 2 this is a singlet, and at 7 this is maybe a quartet. This is what I was saying. It can be hard to tell when you have these very split peaks. It looks like there's 4, but maybe there's 5. It's hard to tell, but again, you use the fragments that are clear, which is like the singlet and the doublet here. And notice that this signal intensity is much higher than this one. So what you would actually have to do if you were given this on an exam is measure these lines here, that this is the integration lines, and then you could determine how many hydrogens are there. This would be done for you, but I just pulled this example out, so I haven't done this, but you can notice that this is about twice as big as that. So maybe this is like 6 hydrogens and this one's like 3, and then this one's 1. You know, I'm just guessing, but that's how you would interpret what you're looking at there. And then it's a matter of piecing it all together. But like I said, you probably wouldn't have to do all of this, piece it all together. What would be expected is like, look at this signal here. How many neighbors does it have, right? And that should be 0 because it's a singlet. So n plus 1 is 1, so n is 0. What about the peak at 1.5? That's going to have 1 neighbor because it's a doublet, so n plus 1 is 2. So that's that. Now I'll move on to a different type of question that you will definitely see. And this one's actually on your homework. This type of question is on your homework for the NMR stuff. So it's determining the number of different, chemically different hydrogens. So there's 2 points here. Chemically distinct hydrogens. So first of all, chemically equivalent hydrogens don't split each other. So that's something like a CH3, CH3. These hydrogens don't split each other because they're equivalent. So they're equivalent because of the symmetry. So this carbon is bound to a carbon that's bound to 3 hydrogens. This carbon is bound to 3 hydrogens. So that's completely the same. So it's like if you go back in your mind when we were doing absolute configuration, it's like distinguishing the groups bound at that center. If they're the same, then it's not chiral. And that's basically the same idea as these chemical equivalents, is if the groups bound to that carbon are the same, then they're chemically equivalent. And if they're adjacent to each other, then they don't split each other. So all we would see in the proton NMR for this is one peak that's a singlet that integrates to 6 hydrogens, because these hydrogens don't split each other. They're exactly the same, so they appear at the same position, and that's why we would get a singlet of 6 hydrogens. But now let's look at a different example and determine how many peaks we would see. So here, I think it's most useful to determine how many carbons of a certain type that you have. So by type, I mean if you have a methyl group, or if you have a secondary carbon, or a tertiary carbon, or a quaternary. In this case, there's no quaternary, but I'll include it anyway. So methyl groups, there's 3 of them, right? Carbon 1, 3, and 5. CH2 groups, there's 1, carbon 4. CH group, there's 1 as carbon 2. So of the methyl groups, are any of them equivalent? And the answer is yes, because carbons 1 and carbon 3 are bound to the exact same position, yielding the symmetry across the position that I've dashed there, right? So what that means is you can't distinguish between carbons 1 and 3. So that implies that they're the same. So there would only be 4 peaks in this NMR, and that means that there's 4 chemically distinct protons because 2 sets of them are the same. Okay, does that make sense? We'll do more examples. This is hard to visualize on the first try. Okay, let's do another one. All right, so again, let's follow my same suggestion. Go through the types of carbons. All right, so carbon 1, 2, 3, 4, 5, number it however you like. So there's no methyls, right? Because of the ring. So none of these. Carbons 2, 3, 4, and 5 are all CH2s. And then carbon 1 is a CH. So now the question is, among our group of CH2s, are any of them the same? Well, we have this plane of symmetry across the carbon at carbon 1, right? Like this one. So what that means is carbon 5 and 2 are the same, carbon 3 and 4 are the same. Because again, you can think about it in multiple ways. You can also think about what's bound there. So if you look at carbon 5, it's bound to 2 hydrogens and then another carbon, and the carbon that's bound to the Cl. Carbon 2 is bound to 2 hydrogens, another carbon, and the carbon that's bound to the Cl. You'll notice those are the same. So carbon 5 and 2 are equivalent. So I just have to rewrite. So 5 and 2 are the same. And then 3 and 4 are the same. So the total number of distinct hydrogens is 3. Because we have these 2 are the same, and then these 2 are the same, and then carbon number 1. So 3 peaks for this NMR. All right, so there is one other thing I wanted to talk about that I completely forgot about until now. I mentioned it earlier, but didn't do it. So hopefully this makes sense. I was hoping to do another example of the chemical equivalent stuff, but I think it's more useful to talk about this other idea here. So there is this thing called exchangeable protons. And exchangeable protons are OHs, NHs, SHs, and so on. We're going to focus here on OHs and NHs. And they can exchange with the solvent. So whenever you do this experiment, you're going to have to dissolve your compound in something like DMSO or DCM or something, some solvent. And this proton is somewhat acidic in both cases. So the solvent can exchange with that. And the issue is that messes with your NMR because your organic compound isn't the same at all times, because that proton is sometimes on that oxygen, sometimes not, and so on. So the best analogy I've ever heard of for interpreting this is if you think about taking a picture of something that's moving very quickly. So like a racehorse or something. If your shutter speed isn't sufficiently fast, then you're not going to get a clear image of the horse. What you're going to get is a blurred image of the moving figure, right? So that's basically the same idea in NMR, is that if your NMR timescale, like your shutter speed of the NMR, isn't fast enough to detect the movement of the protons, then you're not going to get a clear peak. What you're going to get is a blurred image or a broad peak, because the NMR effectively isn't fast enough. It can't keep up with the proton exchanges. And proton exchanges are extremely fast. If they might be the fastest known reaction. Don't quote me on that, but they're extremely fast. They're faster than the NMR timescale, which means that the peaks get broad. So, and they can be at different positions in chemical shift because they're not on the same atom at all times. So that means that when it moves, it's going to affect the chemical shift as well. So that's why both of these can have extremely variable positions, between half a chemical shift to like 6, but they're always going to be broad because of the like shutter speed analogy. So what you're going to see then, it's easy to distinguish these because you'll see a broad peak that integrates to 1 hydrogen, and it's not split, because that hydrogen is bound to an oxygen, there's no other oxygen or hydrogen that can be on that oxygen, so it won't split. So like for instance, this hydrogen right there, there's no other hydrogen on the carbon to split it, and these hydrogens do not split this hydrogen because again it's exchangeable, so it's constantly moving, so the splitting phenomenon cannot occur. So you'll see a broad singlet for the exchangeable proton, and then everything else will be the normal stuff that we talked about, right? So like this is probably a good example to end on, I think. So here we have carbons 1, 2, and 3. Carbon 1 and 3 are equivalent, right? Because the symmetry across the OH carbon, they're the same. So we would see a 6 hydrogen doublet, right? Because those 6 hydrogens are the same. They're both split by the same hydrogen, so they effectively have just one neighbor. And then the hydrogens at carbon 2 will be a multiplet. It'll be a septet, but it's going to be split a bunch. So these would be about maybe 1.5 for the 6 hydrogen doublet. And then this is going to be pretty high, maybe at like 4 because it's bound to the oxygen. And the exchangeable proton, your guess is as good as mine. It's going to be somewhere, but you're going to be able to tell that it's exchangeable because it's broad. So, but this one's going to be like a multiplet and 1 hydrogen. Somewhere around 4. It's going to, again, it'll vary somewhat, but not as much as the exchangeable proton. So, all right. That is it. It's 11:10. So let me know if you have any questions